Le Chatelier's principle, it's a principle that takes a system that is already at equilibrium and then examines how that system reacts to any changes that are put upon it. This concept is what we used in biology. Instead of saying the Chatelier's principle, we use the term homeostasis, but it's the same idea. So you have a system that's at equilibrium, and it has to already be at equilibrium. And then something changes. So either the temperature, the pressure, or the concentration of either your reactants or products. And then we see how the system reacts and whether the KEQ changes or not. So the only thing that will hands down change the KEQ value is the temperature, and that's because KEQ is temperature dependent. So if it's temperature dependent, a change in temperature will change the KEQ value. And one of the ways that you can think about this is back to our Boltzmann distribution curve. Kinetic energy on my x-axis, number of molecules on my y-axis. If I have a temperature, right, this is my distribution of my molecules. Some have a very high kinetic energy, some have a low. This is my average. So if I have the KEQ required for an endothermic reaction, the KEQ required for the exothermic reaction will always be lower. It's always smaller amount of activation energy required for an exothermic reaction. So in general, more molecules in any system will be able to do the exothermic reaction better. However, if I increase the temperature, although the area under the curve increases for both the exo and the endothermic reaction, you can see by the shading, the endothermic is pink and the exothermic is green, that the endothermic reaction increases its area under the curve proportionally much, much more. In other words, the endothermic reaction benefits more than the exothermic reaction does. And the analogy I have is, say that you have $10, which is the endothermic reaction, versus somebody that has $1,000. And for each of you, I give you $50. I increase your pay by $50. The person who had only $10 proportionally increases their amount of money that they have more than the person who had more money. Right? They both increase the number of molecules that can undergo the reaction, but proportionally, the endothermic reaction is favored when a temperature is increased. And vice versa, when a temperature is decreased, the exothermic reaction doesn't get hit as hard. So an example would be an endothermic reaction is evaporation. When the temperature increases, the rate of evaporation is favored over the rate of condensation. As the temperature decreases, it's easier for something to be frozen than it is for something to melt. So keep that in mind. Increase in temperature favors the endothermic reaction. Notice how we're not saying that it favors the forward reaction. It really depends on what my forward and reverse reactions are. And a temperature increase also favors the more entropic state, right? So a greater amount of entropy will be favored when you have an increase in temperature because the average kinetic energy is increasing. So here's an example in which I have a system at equilibrium, and I'm giving my delta H value, or I can show this in the form of where heat is. Both of these are valid ways of showing that this is an exothermic reaction. I have to tell you it either by giving you the heat that's generated or the delta H value. You can't tell that just from your system at equilibrium graph on its own. So here I've increased the temperature, and the endothermic reaction, which in this case is the reverse reaction, is going to be favored. So in this reaction, products to reactants is going to be favored. And so I will see an increase in reactants and a decrease in products. So imagine that my reaction is melting ice, so ice going to water. Sorry, water going into ice is my forward reaction. So if I increase the temperature, my reverse reaction is going to be favored. And so what's happening in this case, because the forward reaction is exothermic, is that my KEQ value will go down. I could have another reaction in which this is an endothermic reaction, and I would show that by having heat either as a reactant or showing that my delta H value is positive. In either way, if I increase the temperature, In this case, my forward reaction would be favored, so I'll create more products at the expense of my reactants, and my KEQ value goes down. So when you're looking at temperature changes, you first have to establish which reaction is the endothermic reaction, and then base your shift based on that. Pressure changes only affect gases, and only if there are a different number of moles of gas on the reactant side versus the product side. So an increase in pressure favors the reaction that has the fewer number of moles of gas. So in this case, this would be the forward reaction. I have 4 moles of gas here as my reactant, 2 here. So if I increase my pressure, my forward reaction will increase, which means I will lose more of my reactants, gain more of my products, and in this case, the KEQ goes down. I can have a situation in which my pressure change doesn't result in anything. So here I have solid carbon plus oxygen gas creating carbon dioxide gas. I have 1 mole of gas on the reactants, 1 mole of gas on the products. So any change in pressure, either increasing or decreasing it, is not going to have any effect on my KEQ because there's not a change in the number of moles of gas from one side to the other. And then finally, I can have a situation in which I have 3 moles of gas on one side and 2 moles of gas on the other side. Sorry, 1 mole of gas on the reactant side and 2 moles of gas on the product side. So if I increase the pressure, the reactant side has fewer moles, so it's going to shift left in this case, as we say. And in this case, I will create more reactants at the expense of my products, and my KEQ will go down. So we use the terminology shift right, shift left in order to talk about which reaction occurs greater or which one is favored. So we simply are taking my reaction, and if I'm moving my reactants toward the products, like this case, so my forward reaction is being favored, we can also describe this as a reaction that is shifting right. I'm moving my reactants and creating products. If I have the reverse reaction in which my reverse reaction is being favored, I'm creating more reactants for my products. It's as if my leftward pointing arrow is taking precedence. We call that a reaction that is shifting left. So shifting left means that my reactants go up, my products go down, KEQ goes down. And in this case, shifting right would mean that my KEQ value goes up. Sometimes a shift left or shift right doesn't change the KEQ value. So if my temperature is not changing, my KEQ value doesn't change. But I may have to respond in a reaction in order to reestablish the right KEQ value. So remember that my KEQ value is my product's concentration over my reactant's concentration. It's a fraction. So I may have to shift my numerator and my denominator. So if I add to either my numerator or my denominator, I may have to change things around in order to create an equivalent fraction so that my KEQ value doesn't change. So for example, here's an example in which I've increased the concentration of reactants. So I have a system that's equilibrium and I'm dumping more reactants into it. How do I know that I've dumped something into it? There's going to be a hump where I have added that, and the other thing will stay the same. Okay, so whenever you see a hump somewhere and something staying the same, that means that whatever I have the hump of is what I added. So now I momentarily have too many reactants. My denominator is too high, and my products didn't change. So I have to move things around to create the equivalent fraction. So I have to lose some of my reactants and gain some of my products, just sort of shifting it. So if you think about it as a balance, right, a seesaw, where I have something at equilibrium, just the right balance, and then I add more to this side, I'm going to have to shift things over to this side in order to reestablish that balance. That's that shifting left. So in this case, I am shifting to the right, meaning I'm moving some of the excess reactants and creating products in order to keep my KEQ value the same. So in the end, both of these concentrations are higher than my original concentration in a proportion that maintains that KEQ value. So again, if I added something, I will see it as a hump in what I added. The other thing stays the same. Then it's going to shift in whatever way to re-achieve the balance, and both of them in the end are going to end up with a higher concentration than they had before. I can also take out reactants. In that case, I would see a divot, which is the opposite of a hump, and the other thing will stay the same. In this case, I have taken out some of my reactant, so I need to restore some of the reactant, and that can only come from my product. So I will gain some more reactant back at the expense of my products. It shifts left to regain the balance. And here in this case, both of my final concentrations are going to be lower than the original concentration. So if you contrast that with when the KEQ value changes, when a KEQ value changes, one will go up, one will go down. Either the reactants will go up and the products will go down, or the products will go up and the reactants go down. When the temperature doesn't change, but I still have some sort of reaction, either both of my reactants and products will go up, or both of my reactants and my products will go down from their original concentrations. And this is just another way of looking at it, but this time I'm changing the amount of product, right? So in this case, you're looking at my products here, and my product concentration increases because that's where the hump is. This one stays the same. My reactants are always starting at just reactants and no products. And so this is going to go down. This will increase. So what I've done is I've created more reactants. I'm shifting to the left. But in the end, both of these final concentrations are greater than what they were before I made the change. KEQ doesn't change. And here's an example in which I've taken out some of the product, and you can see that with the divot. My reactant stays the same. So in order to reestablish that, I have to create more product at the expense of my reactant. Both of these values are lower than both of these values right here. So again, they both go down proportionally so that I create an equivalent fraction. Right, so it's as if I went from 6/4 to 3/2.